Hi, I'm Bob Smith, the founder of Demand Peripherals. This video is an introduction to our FPGA-based automation controller. If you've done automation work before, you know to expect the hardware will have user interface components, sensors, and actuators. There'll be a real-time controller, typically a microprocessor, but in our case, an FPGA, and Linux software that provides a link to the real-time controller on one side and has an API to your high-level application on the other side. In our system, we've taken 32 pins of an FPGA, routed them to 4 connectors, and then to Y cables. At the end of each Y cable is a connector that has 4 FPGA pins, 2 grounds, 5 volts, and 3.3 volts. The power lines are interwoven with the FPGA lines to help reduce crosstalk on the FPGA lines. The connectors go into daughter cards, and you can choose whatever daughter card you want. Changing the wiring is as simple as unplugging one daughter card and plugging in another. We have a wide variety of daughter cards. We have about 30 designs. They're all open source, and you can buy them on our website if you want. Because they're open source, you can include the designs in your own circuit, or if you wish, you can design your own circuit right from scratch. If we look inside the FPGA, what we see is an address and data bus, and then what we call slots, where Verilog modules can hang on the address bus at a particular address. Each module goes out to a specific 4 pins that then goes off to the interface card. In this way, you can match the Verilog peripheral to the interface card, the daughter card that you're using. You can build your own FPGA image. We have all the source code available on GitHub, or you can go to the Demand Peripherals website, select Support, and then build an FPGA image from that. It'll step you through how to specify what peripherals to include in your FPGA image. We'll build it and email it to you, and there's no charge for that service. To me, the best part of the whole system, though, is our Linux software. The application program interface consists of lines of ASCII text over a TCP connection. Each line contains a command of the form command name, peripheral name, resource name, and optionally a value. dpset writes a value, dpget reads a value. dpcat starts a stream of sensor data over the TCP link. dplist lists the peripherals available in the FPGA image. There are bash equivalent commands for each of these API commands. If you use dplist with a peripheral name, the bash command will print a help text for that peripheral. All of this is available on GitHub. Let's take a look now at a sample application. Our sample application has a single board computer, a 5-volt regulator, a power distribution card, the FPGA card, an IR receiver transmitter, a 6-digit LCD display, a dual H-bridge, and 2 GPIO cards, one to control some NeoPixel LEDs, and one to take the input from the quadrature output of the motor. Let's open up a couple of X terminals and take a look at the API on some of these peripherals. We've opened 2 X terminals and secure shelled into the single board computer on each. The program that provides the API is dpdaemon. Install dpdaemon with the usual git clone, make, sudo make install. Run dpdaemon. Typically with the -L option to specify the binary file to load into the FPGA. dpdaemon is a true daemon. It goes into the background and disassociates from its controlling terminal. This command is the command you would normally use in your init scripts. dplist, we saw, should give us a list of the peripherals in that FPGA image. In the DP list, we see the peripheral names, and we see the control points that let you access the data or the action just associated with the peripheral. We mentioned that the API is Telnet, is TCP-based. So let's try Telnet to open up a raw TCP connection. DP set, LCD 6, display. And sure enough, we see the display update. In the raw protocol, the command line interpreter returns a backslash to indicate that it's ready for a new command. Your program, once it's issued a command down the TCP link, will have to watch for this backslash, but not just a backslash. You might also want to look for an error response. But whether there's an error or not, the backslash will indicate that the command interpreter is ready for a new command. We had said that there was bash equivalents for all of the DPI commands. Let's try that. And sure enough, we see the display update again. The bash commands return an exit code that indicates whether or not an error occurred. As you would expect, you get a 0 return code if there was no error. We mentioned that dpcat is the command that starts a stream of sensor data. Once the dpcat is issued, that TCP connection is dedicated to receiving data from the device. Note that the data will always be ASCII formatted and terminated by a new line. One of the nice things about dpcat is that it implements a lightweight version of what is called a publish-subscribe system. This means that you can have multiple programs all listening for the same data. For instance, if you had a quadrature decoder tied to your motors, you could use that for motor speed control, but you could also use it as part of your odometry system. Let's review. Demand Peripherals uses an FPGA to implement the peripheral hardware. This means Linux talks directly to the peripheral hardware. There's no microcontroller in the middle. Even though we use an FPGA, typically you won't need to do any Verilog. We even build the Verilog image for you. We have over 25 different Verilog peripherals available that are all open source. We also have open source daughter cards that show you how to use the hardware that you might want in your own system. Of course, you can buy our daughter cards online if you want. To me, one of the nicest parts of this system is the API. It uses lines of ASCII text over a TCP connection. And all of the commands have bash equivalents, so you can explore and test your system from the bash prompt. We've got a very simple publish-subscribe system in dpcat. If you've ever done low-level programming for dbus or ROS, you'll appreciate the idea of having a publish-subscribe system that is ASCII text over a TCP link. Given all of the above, you'll find that you can do your hardware design faster since we have open source hardware, and your software design, coding, and testing will be much easier since you've eliminated the microcontroller. Perhaps the best part of this is that you'll have improved reliability. Microcontroller software is very tricky in terms of interrupt collisions and real-time constraints. Verilog, on the other hand, can be tested fully using usually not much more than an oscilloscope. While everything we have is open source, we're quite happy to offer commercial support, and we can help you with your designs. My name is Bob Smith. I'm the founder of Demand Peripherals. Thanks for watching.